So it's my great pleasure to present you Andy Mackenzie. So Andy Mackenzie made his PhD in Cambridge, then he was in Birmingham, and then he was for a long time in St. Andrews. And I met Andy quite some time ago, right?
Yeah.
It was so I had to do, I was in Grenoble and I was working on Strontium luthenate, and we had to put some contacts on the sample. And I was told that there was a very good group who makes excellent single crystals and who makes very nice and carefully very small contacts in small samples. So I went there for a few days, and well, it was kind of nice, and I learned many things. And I think that since then Andy has been exploring this view to make experiments which may be classical in the sense that resistivity, thermal experiments, but always on the best possible samples and on very good samples and with an accuracy which remains unsurpassed in many cases. So, and 1 year he has been in Dresden, he has accepted their position there, and he's setting there up a new group. So it's really my pleasure to have you here, Andy. Thank you very much for coming.
Okay, well, thank you very much for the invitation and for the excellent hospitality, both now and later on when we're off to see the football this evening. So, what I'm going to talk to you about today is using a title that Herman gave me. Okay, so I'm going to give you something of a review talk about a field that we have a little bit of presence in. We do some work in this field, but I certainly want it to be a colloquium style talk rather than a seminar, so I deliberately don't emphasize our own work particularly strongly in there. It's on a subject called electronic liquid crystals, which is a very topical subject, and so hopefully if I give you some of the background to it, my aim is to give you an impression of why so many people have become interested in this field over the past 5 to 10 years. So specifically what I'm going to try and do is to give you an introduction to standard classical liquid crystals, and then move on to the possibility of quantum liquid crystals of electrons in solids. Then I'll give these experimental examples. These effects were first seen convincingly, I think, in high purity gallium arsenide-based two-dimensional electron gases. One of the great reasons for interest is the appearance of apparent electronic liquid crystalline states in the same phase diagrams as both the high temperature superconductivity in the copper and iron-based superconductors. The material that we stumbled on, which has led to us doing some work in the field, is strontium-3 ruthenium-207. So I'll mention a little bit about what we've done on that, but then particularly emphasize a really excellent experiment that's come out in the last couple of months from Bristol, which is changing the way we think about this material somewhat. But then I'll move on to probably part 3 here, would be the part where many people in the US would tell you that electronic liquid crystals are of the highest significance. And that's because right throughout the talk, I'll make an analogy between particle-particle pairing in superconductors and particle-hole pairing in unconventional magnets and some of these electronic liquid crystal states. And what people are trying to do is to search for leading order instabilities in both the particle-particle and particle-hole channels to try and see if they can come up with a new set of model Hamiltonians that will help them understand both the fields of crystalline states, liquid crystalline states, and the field of superconductivity. So I'll give you a few very recent archive references to that kind of work that's going on, and then I'll just try and draw a few conclusions. Now, I participated as a very minor player in a review article that was written in 2010, mainly by Eduardo Fradkin and Steve Kivelson. But this was about one particular form of electronic crystal, the electronic nematic, and that's deliberately written in quite a didactic way. So if you are interested at the end, I would recommend that you go and have a look at the introduction to that paper. Have a look at the introduction to that paper to get a better feeling for some of the things I've said. Okay, so in the spirit of a colloquium, let's go right back to the beginning. What is a liquid crystal, just in a classical sense? Well, it's some form of a structured liquid. So if you have a non-structured liquid, just an isotropic liquid, that's the highest symmetry state you can imagine in terms of the bulk symmetries that would explain the properties of that liquid. If, however, the liquid is made of some form of shaped molecule, sometimes called an nematogen, then it can be advantageous. Now, I should have tried to draw randomly oriented nematogens in this one, but it was too hard to draw, so just imagine they're in there. At some point, though, if these nematogens exist, it can be energetically favorable, and particularly entropically favorable, for these things to end up lining up. And these are often entropy-driven transitions because when the molecules are in all random directions, there's a lot of internal degrees of freedom of the molecules that they can't explore. So the entropy actually rises of the system when they go into the slightly ordered state where they free up their ability, they've disentangled themselves, and they've freed up their ability to undergo internal transitions. By definition, it's a nematic liquid crystal if it has orientational but not translational symmetry breaking. So it's a lower symmetry beast than the isotropic one, but it's the sort of minimal symmetry breaking that can go on. The next type of liquid crystal that's well understood is called the smectic liquid crystal. And here you have a further symmetry breaking going on because you've gone from the completely isotropic symmetry to both orientational and translational symmetry breaking. Okay, now one of the important things to realize about electronic liquid crystals when we come onto those is that the experimental signature you typically pick up is very difficult to disentangle from being a nematic or a smectic. So in general, you'll pick up some orientational dependence of the properties of this electronic gas. But unless you're able to do a diffraction experiment which is sensitive enough to pick up the translational symmetry breaking, you might presume you have a nematic when in fact you have a smectic. And you've always got to be worried about saying something is definitely a nematic because you didn't see the extra symmetry breaking that would make it a smectic. So every time you're reading about a nematic in the literature of solid-state physics, I think you have to be careful to realize it might only be a nematic for a certain amount of time until a smectic transition or a smectic ordering is then discovered in it. And actually, I'm going to give you a good example of that today. So this is all the classical liquid crystals that De Gennes and others famously worked out the theoretical understanding of back in the 60s and 70s. In about the late 1990s, Steve Kivelson, Eduardo Fradkin, and the late Vic Emery wrote a very influential paper in Nature based on concrete modeling from the Hubbard model, but on the basis of those modelings, of those models where they discovered some translational symmetry broken metallic states, they specifically asked the question, is it going to be productive to draw the analogy with liquid crystals for what could happen for electrons in solids? And we again have to be a bit careful here because some of what's gone on is rebranding. Right? Some of the states that we would now call a nematic liquid crystal state, as I'll show you, were thought about 50 years ago. Other smectic states were thought about 50 years ago. In general, though, I think the reclassification has been more helpful than unhelpful. And it's now become widely used in the field. And it's undoubtedly true that there are both nematic and smectic states that have been discovered, which are, in theory as well as experiment, which are genuinely new. They aren't just a rebranding of states that we had before. Okay, and what does it say down there? Yes, the other important thing is to say that in the electrons in solids, you're dealing with, of course, with point electrons, so you have no obvious nematogen. You don't have quite the same analogy of some electron molecule that's going to be needing to order. Some of the states you see might effectively involve short-range construction of electron molecules, but the fundamental reason for any of this is the electron-electron interaction. This is going to be interaction-based, so it has to be some peculiarity of the interaction that leads to a susceptibility for this kind of state. The other thing I didn't say at the start of the talk is it's absolutely fine with me if you'd like to ask questions during it, so don't let me say completely incomprehensible things without stopping me. So, winding the clock back, all the way back to 1959, over 50 years ago, just in the first couple of years after Landau proposed his Fermi-liquid theory of interacting metals, a lot of his colleagues, possibly motivated by him, started publishing papers about what the limits of Landau's Fermi-liquid theory were going to be. So you may remember, or you may know, that in a Fermi-liquid, you have a very strange and beautiful theory which is perturbative in the distance that you are from the Fermi surface, but it's not perturbative in the strength of the interaction. So in principle, Landau came up with this wonderful theory that said that a liquid of strongly interacting electrons would still have a Fermi surface and would still have many of the properties of the non-interacting electron gas, as long as you recast the electrons into many-body quasi-particles that incorporated some of the strong electron-electron interactions. And the great thing about the theory is that in principle you can crank that bare electron-electron interaction up as high as you would like, and as long as the criteria, the other criteria for the stability of the Fermi liquid are satisfied, you'll still be able to make the Landau transformation. The perturbation comes in the fact that you can only do that transformation at lower and lower temperatures, the stronger and stronger the bare interaction. However, and what Landau then also did was to recast the bare interaction in a series expansion of a quasi-particle interaction in a series of things that you measured phenomenologically called the Landau parameters. And as long as these Landau parameters stay well controlled, even if the bare interaction gets hugely strong, you still end up in an isotropic system with a circular Fermi surface. So in exploring the limits of this, really in a phenomenological way, Pomeranchuk wrote a famous paper where he noted that if you could find physical circumstances to make some of the Landau, one or more of the Landau parameters negative and large, beyond a certain critical strength, you could have the Fermi liquid being unstable to various, to a certain type of instability, which would be a shape instability. So he didn't give any microscopic justification for why this would happen, but he just pointed out that there were channels where the Landau Fermi liquid could break down in an anisotropic way, so you could, in one of the Pomeranchuk channels, have a circular Fermi surface distorting to become an ellipse. And he and others then noticed that this kind of instability would depend on details of the quasi-particle dispersion, details of the many-body interaction. There were some kinds of pathological interaction that you could write down that would cause this to happen, rather than Fermi liquid theory to be stable as Landau originally proposed it. So this ellipsoidal, spontaneous lowering of the symmetry from circular to ellipsoidal is giving you a preferred direction, but it's clearly also not giving you any translational symmetry breaking. So this, by definition, is the first prediction of an electronic nematic in the language of liquid crystals. And it was done all the way back in the 1950s, and people have been looking for it ever since. I mean, people were studying for many years. And it was actually almost exactly 40 years after this prediction, I think, when people saw the first generally accepted example, and I'll come on to that later. So as I mentioned in the motivation, the analogy between these liquid crystal states and unconventional superconductivity is quite useful if you've been used to superconductivity like me, and it's also becoming even more useful for reasons we'll get onto at the end of the talk. So what people do is they say, well, we'll think of, say, the Pomeranchuk instability as a kind of particle-hole pairing. And what you mean by this is the following. You've got your circle, you change it into an ellipse. In doing that distortion, you've created extra electron-like states in two directions and extra hole-like states in the two orthogonal directions. So if you were looking at the gap function of a D-wave superconductor, it would be particle-particle paired, but the superconducting condensate would have a plus phase there and a minus phase there. So instead of a phase reversal associated with particle-particle pairing, you have a carrier-type reversal looking like particle-hole pairing. And this, in many ways, you could think of as an extremely complicated way of viewing a circle that changed to an ellipse, right? But it comes in, our theory friends love it, because you can write down a formal order parameter expansion in powers of this parameter L, and L equals 2 corresponds to that distortion there. So in the language then, this is an electronic nematic is a D-wave distortion in the particle hole channel. And so this can be justified in formal grounds as well as just something that you wave your hands about. So that's one limit of how you could get an electronic nematic, this Pomeranchuk instability. The second limit is to imagine we had some very strong interaction that had caused our electrons to organize themselves into some smectic or stripy phase with long-range translational symmetry breaking. So examples of this would include, in all honesty, they would include a standard charge density wave in a system that wasn't fully gapped. That would now be classified as an electronic smectic. You would have translational charge density symmetry breaking. Some of the states that come out of the Hubbard model involve simultaneous charge and spin ordering in rather complex patterns and channels down which the conduction can take place. But these would all be examples of smectic phases. But these smectic phases, particularly in low dimensions, may not be stable, and what they might do is to melt in the same way that you imagine solids melting towards liquids. In fact, I was just talking earlier on about topological defects coming into vortex lattices. Well, the way this would melt would be topological defects coming into the stripe phase and giving you something which had texturing and orientational order, but if you tried to do a diffraction experiment, you would get no long-range symmetry breaking from that diffraction experiment. And again, for some people, the superconducting analogy might be quite helpful. This would be a weak coupling nematic. This would be a strong coupling nematic. The weak coupling things you look at in K-space, whereas the strong coupling things are easier to visualize in real space. And in terms of superconductors, the analogy would be that this is like a BCS limit of a nematic, and this would be a bit like a BEC limit of a nematic. So, so this, I think, in many cases, this language is helpful.